All right. Hello and welcome everyone to our Nuclear Fusion Great Potential and Challenges webinar to discuss the status of fusion technology in Canada and around the world. My name is Rachel Roberts and I am the Program and Services Associate at OCNI and I will be your technical lead for today. Please note that this webinar will be recorded. If you have any questions during the presentation, please add them in the chat window that is accessible by clicking the little chat bubble at the bottom right of your screen. I'll now hand it over to our event host, OCNI's President and CEO, Ron Oberth.
Thank you, Rachel, and good afternoon to our guests from Ontario. Good morning to our many guests from Western Canada, and good evening to our guests from Europe. And if I've missed any part of the daily calendar, I apologize. This is OCNI's first ever nuclear fusion event, so it is kind of a very special day in our calendar. Experts speak of nuclear fusion as creating a star on Earth. This is not easy. I'm sure it doesn't even sound easy, but our distinguished speakers today will tell us how to do that. And we look forward to learning about this amazing conquest of nature that has been a pursuit of scientists and engineers for at least 50 years or more. But I note that our fusion experts today all have either connections to or are based in Alberta. So in fact, Alberta is becoming kind of the center of the Canadian fusion galaxy, in addition, of course, to Burnaby, BC, because I know we have some guests from General Fusion on the line. And I also note the coincidence that just last week, the Premier of Alberta signed on to the Small Modular Reactor MOU with Ontario, New Brunswick, and Saskatchewan. So we suddenly see Alberta emerging not only in the SMR business, but we're going to learn about Alberta's work in fusion by some of our esteemed guests this afternoon. But first of all, let me just say that I'm also proud to announce today that OCNI and the Fusion Energy Council of Canada, as represented today by Dr. Axel Meisen, signed a memorandum of understanding on March the 11th of 2021, in which we will collaborate in three broad areas: communicating the benefits of fusion energy to public audiences in Canada, which we are doing partly today with some members of the public who have joined us, encouraging technical exchanges among Canadian fusion specialists and members of the Canadian nuclear supply chain, which OCNI represents, and hosting joint technical and informational seminars and webinars on fusion energy, today of which is the first one, but it's only the first one of two, and you'll hear more about this as we proceed. So it is now my pleasure to introduce my good friend and colleague, Dr. Axel Meisen, who is the interim president of the Fusion Energy Council of Canada. Axel was the inaugural chair in Foresight at the Alberta Research Council, a very proper name for an organization that's looking far out into the technical developments of the future. Axel has had a very distinguished academic career. He was president of Memorial University in Newfoundland. He was dean of applied science at the University of British Columbia. And most importantly, and for which I will heartily congratulate you today, that he was appointed to the Order of Canada in 2008. So we were very privileged to have Dr. Axel Meisen and also a member of the Order of Canada who will lead today's discussion. So I'll turn it over to you, Axel, to introduce your other colleagues in the program and to lead us through this exciting presentation about fusion here and around the world. The floor is yours.
Thank you. Thank you very much, Ron, for your welcome and also for having arranged today's webinar. We in the FECC feel privileged to participate in today's events. And like OCNI, we in the Fusion Energy Council of Canada look forward to collaborating with you. Today's webinar is a tangible manifestation of our collaboration under the Memorandum of Understanding that our two organizations signed recently. I will introduce two of my colleagues in the course of this webinar. The purpose of today's webinar is to introduce fusion energy and its implications. And based on the information provided by registrants, their knowledge of nuclear matters differ quite widely. Some have detailed knowledge, typically grounded in nuclear fission. Others only have general knowledge, but are curious about nuclear fusion and its potential. To meet these diverse needs, we've divided the webinar into three major sections. The first section gives a general overview that utilizes a familiar analogy. The second section provides important scientific and technical details that should appeal particularly to nuclear experts. If you're not an expert, don't worry. The details are not essential to follow the strategic perspectives that are given in the third section. And as Ron said, we will conclude the webinar with a question and answer session. This will give you opportunities to raise points of a particular importance to you. So may I have the next slide, please? Could I have the next? Thank you. Let me start with an analogy that should help to understand fusion. The analogy I've chosen is that of human flight. Birds, butterflies, dragonflies clearly can fly. It is therefore not surprising that humans have also thought about flying. Next. The myth of Icarus, dating back some 3,500 years, describes his attempt to fly by using feathers stuck to his arms. The attempt failed, supposedly because the wax melted as Icarus flew too close to the sun. As we now know, this was the wrong reason. However, it did not deter many others, including Leonardo da Vinci in the 1400s, to conceptualize a flying machine based on flapping wings. Again, this failed for fundamental reasons of physics. Then there was the attempt to fly using lighter-than-air balloons. This worked, but it was unwieldy because the direction of flight was dependent on wind direction. This made it impractical. Next slide. The real advances in human flights came at the start of the last century, when the Wright brothers understood that lift could be generated by forward motion, and forward motion could result from thrust of propellers powered by a suitably light internal combustion engine. Their first flight spanned no more than a few hundred meters, but the essentials of lift and thrust were proven. Next. It then became a matter of applying and refining these essentials. This received enormous impetus and governmental support in World War I and II, thereby making human flight possible as we know it today. It all occurred within about a century of the Wright brothers pioneering flight. Next slide, please. And thus, it can be with fusion energy. As with flight, we know that energy from fusion exists, occurring in the sun and in other stars. Fusion creates enormous amounts of energy. We also know that fusion is based on light atoms and tremendous temperatures. In stars, it also involves extraordinary pressures created by their gravitational forces. However, as our present knowledge of physics indicates, extraordinary pressures are not essential for fusion. Next. To replicate the fusion process occurring in the sun and stars, we are now engaged in attempts to make it happen on Earth and under controlled conditions. As in the case of early flight, the equipment is complex and cumbersome, without having thus far resulted in sustained net energy production. We can think of today's fusion devices as the Wright brothers' planes about 100 years ago. Next slide. Let us now take a brief closer look at nuclear fusion and compare it with nuclear fission. The left image shows small nuclei of deuterium and tritium being forced together to fuse, thereby forming an alpha particle or helium and a neutron. As shown on the right, In nuclear fission, a large nucleus is broken into smaller nuclei due to the bombardment of neutrons. Next. In both cases, there is a change in mass, with the mass being converted into energy following the well-known energy equals mass times the square of speed of light equation. Next. Before I give more details, let me indicate the notation used for the various species involved in fusion reactions. The small numbers next to every species indicates the numbers of protons and neutrons. Next slide. We can therefore represent the fusion reactions of deuterium and tritium by the first equation on this slide. Deuterium can be obtained from seawater and from fresh water, but tritium must be on hand to start the fusion reaction, and it must be produced to sustain the reaction. And the latter can be done by impacting the neutron from the first reaction with lithium nuclei. The overall reaction is therefore as shown. In other words, deuterium and lithium are the raw materials to produce helium and energy. Some of you may not be familiar with energy expressed in electron volts, abbreviated as EV, and the letter M stands, of course, for mega or million. Next. To make this more meaningful, I have converted the energy units. For example, 1 kilogram of deuterium would require 3 kilograms of lithium and produce, under ideal conditions, 300,000 megawatt hours of energy. This is equivalent to the energy content of about 135,000 barrels of petroleum. Next slide. We can also look at this from another perspective, namely, how much deuterium and lithium are needed to produce energy equivalent to 1 million barrels of petroleum. The answers are shown in this slide. 7.4 kilograms of deuterium and 22 kilograms of lithium. Next, please. This slide also shows a tanker loading 1 million barrels of petroleum. Compare its size with the small volumes of deuterium and heavy water and lithium. This makes a compelling case for the potential of fusion energy, but much more needs to be understood. In a moment, let me now hand it over to Robert for a more in-depth portrayal of scientific and technical issues of fusion. By way of brief introduction, Robert Fedosejevs is a full professor in the Department of Electrical and Computer Engineering at the University of Alberta. He specializes in laser science and physics with great relevance to nuclear fusion. Robert?
Thank you, Axel. And just before I continue, Rachel, there's a gray box on my screen on the right-hand side of the slides. I don't know if others are seeing that. That obscures.
That gray box should be the videos of you guys speaking. It might just be your bandwidth trying to keep up with the video.
No. Okay, I have the videos on top. So as long as nobody has an obscured slide, that's fine. Okay. Then
it's on mine as well.
Yeah, I think it's when you open your video, it overlays, I think. And it might cover some material. That's all. If you can minimize it and move it up. It's there. That's better. That's better. Yeah, it's now aligned. Okay, good. Okay, so next slide, please. So let me continue from where Axel had left off and enlarge the scope of fusion reactions which are available. In fact, there's very, very many of them, but these are just the ones that are most accessible. And Axel highlighted the main one, which is deuterium-tritium, which is reaction 1 here as ABC, as the subreactions, which have a net production of energy on the order of 20 MeV. I'll point out there's a second tritium production reaction, which involves fast neutrons, which involves lithium-7, so that's 1C, where the neutron gives up energy, 2.4 MeV, but in the process also produces tritium and an extra neutron. So in fact, this is useful for the neutron breeding process to get a multiplier factor slightly over 1, so that one can ensure that one gets a net production of the tritium greater than unity as you consume it. The other reactions, then 2A, B, C, those are the deuterium reactions, and you can just use deuterium and form tritium and helium-3, and then the deuterium can react with the tritium and also the helium-3 and produce energy in this cycle. Finally, there's the deuterium and helium-3 reaction 2C, which produces just helium and protons. And notice when you're finished in all these reactions, you're ending up with the innocuous helium as your byproduct. And so, in fact, it doesn't produce any radioactive waste in the process. There's another reaction of current interest, which is the proton, or it's been long-term interest, proton-boron fusion, which is reaction 3, where proton reacts with boron-11 and produces then 3 alpha particles, the helium-4, when ionized are alpha particles plus energy. And each one of these successive reactions has higher and higher thresholds, as I'll point out in a few minutes, in terms of exciting them in order to get them to actually occur in a controlled fashion. We certainly understand the physics of all these interactions quite well from all the fundamental studies that have been undertaken over many, many decades. But in order to produce net energy, we have to have these reactions ongoing in a controlled fashion, where the net energy produced is more than the energy we invest in actually making the reaction occur. I will point out the attraction of 2C and reaction 3 is that they don't produce any neutrons. And so, in fact, they give us the cleanest potential fusion reactions, which will then be neutron-free, won't activate the structures, and we can take the charged protons and alpha particles that are produced. And in fact, in using various methods, we can convert that energy directly to electricity, decelerate them in potential fields, extract the energy, and therefore make a much more efficient reactor. But these have much higher thresholds and probably will be generation 2 or 3 fusion reactions in the future. Okay, as was pointed out, the fusion reactions release about 1 million times the chemical energy per nucleus, and so it gives us a tremendous energy yield for a very small amount of fuel. Next slide. Okay, so what's the difficulty? Well, the main difficulty is that we're talking about getting the nuclei together with charged particles. So unlike fission, where you have a neutron which is not charged, which can easily wander into a nucleus, you have now 2 charged particles which have to come together close enough so the strong nuclear force will overtake and cause the combination and the fusion process, which means you're facing the Coulomb repulsion of 2 positively charged species, which have to get extremely close together. And the energies require that those species have energies on the order of 10 keV per particle up to 100 keV or more. And this corresponds to temperatures which are on the order of 100 million degrees Kelvin, which is, you know, a mind-boggling temperature. I mean, these are temperatures which are higher than in the sun, essentially. At those temperatures, of course, all matter is ionized to form what's called a plasma. So here we have ions and electrons freely moving around each other. And therefore, we have a very complex system of charged particles with electromagnetic interactions, with interactions with magnetic fields, which we then use in order to trap them. And so that's a plasma. And the other factor is, of course, when they have this energy, they are moving at extremely high velocities. And so they can easily escape in a matter of microseconds. So we're talking about energetic particles with, for example, deuterium at 10 keV per particle is around 10 to the 6 meters per second. And so, you know, confining that for seconds means you're going to have to keep it from running away many, many times every second. And so we need very good confinement mechanisms to ensure that we can get the net energy out that we invested in heating the system to begin with. And so this is what's called a burning plasma. To maintain the plasma, we need confinement mechanisms. At the same time, we would like to initiate some type of a burn wave where we actually use the alpha particles, which are created in many of the fusion reactions, to redeposit the energy. They are stopped more efficiently within the fusion fuel itself, and they can actually act as a burn wave going through the fuel. And so this, in essence, gives you one mechanism of maintaining the hot plasma as long as you can confine it. Next slide, please. Okay, so what you need to start with is then what is the reactivity of the species? And I won't go into details. I just want you to understand that from this plot, the various curves give you the effective reactivity. That's the cross section for the reaction times the average velocity of the species. And essentially, we want to use that to calculate how many reactions per second per cubic volume we have. And that's on the upper right. The power in the fusion release is the number density of deuterium times the number density of tritium times this reactivity rate, and times, of course, the energy released per fusion reaction, the 17.6 MeV for the basic deuterium tritium. And so we look at this curve and we can get the numbers here, which by themselves don't mean too much. But one thing is that this is a function of temperature, the particle energy, as we said, that has to be high enough to collide. And so if you look at the temperature scale on the bottom, you notice this is billions of kelvins. So you're in the range of 100 million to a billion degrees Kelvin. Or what's more useful from the particle point of view is the average energy per particle, which is in the range of 10 keV to 100 keV. And so that means we need very hot systems, as I mentioned. Okay, next slide. In converse of that, we can then look at what are the criteria that we need to meet in order to get net energy return. And I'm not going to go into details, but by going through the calculations to release more fusion energy than the losses and the energy invested in heating, you basically come to a conclusion which all hot fusion reactions must obey in order to get net energy gain, and that's the so-called loss and break-even criteria. And this is essentially the product of the density of the reactant species, the plasma density, times the confinement time of the energy you've invested. So how long it takes for that energy to decay away must be greater than some number, and that depends on the reaction and the temperature of the system. But for deuterium tritium, that number at its best is around 2 × 10⁻20 seconds per meter cubed. And that's illustrated on the curve to the left, the blue curve where you see versus the species temperature, there's a minimum on around 2 × 10⁻20 at a few hundred million degrees Kelvin. If you look at other possible reactions, such as deuterium-deuterium, you see that they require much higher conditions. So the criteria has much higher threshold for deuterium helium-3. It's also higher by about an order of magnitude in temperature and almost in density. So essentially the DT reactions require this minimum criteria, which any approach to fusion will have to satisfy, whether it's magnetic confinement, inertial, as we'll get to. Next slide, please. Okay, so essentially, as mentioned, we need high temperature, we need confinement, loss and criteria. Therefore, we can look at different approaches. One can look at not very, but somewhat dilute systems at long time scales, and that leads us to many of the magnetic confinement schemes, so magnetic fusion energy, MFE. Or we can go totally in the opposite direction and say, let's try to make this very, very fast and intense and have all the reactions occur before the fuel can disassemble, in which case you need to heat it very, very rapidly, extremely rapidly. And those are the inertial fusion energy schemes, such as laser-driven fusion. And I'll get to that in a sec. So we can go to the next slide. So if we look at magnetic confinement, well, basically magnetic confinement works because the particles orbit around magnetic field lines. Basically, whenever a particle tries to cross a magnetic field line, it starts to curve its trajectory, the V cross B force, and that will cause it to orbit. And so whenever we have magnetic field lines in a system, you can think of the particles spiraling back and forth along those lines. And they're essentially trapped on those lines. And we can then think of various systems to try to use magnetic fields to confine the particles. And one of the simplest is a solenoid type mirror machine, as it's called, on the left, where you just have magnetic fields with stronger fields on the ends to try to confine the particles. And very simple, but it's leaky out the ends and very difficult to meet confinement conditions. Then you could say, well, let's connect the ends together and make a circle out of it. And that's the toroidal approach, or the tokamak approach, as indicated in the middle, where you can have a torus. And in principle, the particles spiral around and around forever. And so in simple-minded concepts, you could trap the particles forever. A more complex configuration, which I'll get to later, is the stellarator. Just to touch on that, I'll go to the next slide, please. So just to give you a sense for the complexity, as I said, we have magnetic fields, electric fields, ions, electrons. Essentially, the equation of motion is given here in the box for the particles, which indicate the various motions parallel and perpendicular to the magnetic field, the effects of the electric and magnetic fields, E cross B drifts, time-dependent drifts, gradient B drifts. I won't go into details, but just to show you that this is not a trivial problem. It has many complexities to it and easily lead to escape modes for the particles, so-called instability modes of various sorts. And so if you just think of the simple toroidal system that I showed you earlier in cross-section on the bottom, what one finds almost immediately, and was discovered in the early 60s and late 50s, was that as the particles go around the torus, the gradient of the magnetic field causes the ions to drift upwards, the electrons to drift downwards, and then that causes an electric field to build up, and that electric field combined with the magnetic field gives an E cross B drift, which then causes all the plasma to move to the outer wall, and your plasma is finished. And so it was discovered that this, in its simplest form, was not stable. Go to the next slide. However, a solution was found when one adds a current to the plasma. So if one actually makes this plasma toroid, as shown on the left, part of a transformer system where you're actually inducing current to flow through that. Now our plasma is effectively a secondary winding of this transformer. Induce a current in that plasma. That current produces an additional colloidal magnetic field, just like the current around a conducting wire, the magnetic field around a conducting wire. So that field will act together with the original solenoidal donut field that you had and produce a spiraling field. And that spiraling field will twist the plasma motion, just like a rifle bullet. And that spinning stabilizes the plasma. So as it tries to drift outwards, it's also spinning around. And so what has drifted out a little bit spins around and becomes the inside, and therefore starts drifting the other way. And so by doing so, spinning it fast enough, it stabilizes the plasma. And that's the concept of the tokamak devices, which is the mainline leader in terms of magnetic confinement devices being considered today. And so that's just illustrated on the right here. So next slide, please. Okay, so if we look in a bit more detail, again, in the cross-section of a tokamak type device, we have the electrons in blue in the middle, spiraling around the field lines in one direction, the ions in red spinning around with bigger orbits, and those then, in theory, can be confined indefinitely, but of course there are still collisions and plasma instabilities which occur, which cause loss and diffusion of energy outwards. And so those are your loss mechanisms that you're fighting. And the net goal, as shown on the left in the equation, the red equation, is to produce net energy out relative to the energy you've invested to set up and heat this system to begin with. And so a major parameter that one always looks at in the design of these devices is the Q parameter. That is the power out versus the power in. And of course, the goal is to clearly get Q as large as possible. And initially, one needs to demonstrate that indeed you can even get a Q greater than 1, which is still the first goal. And then in the near term to look at Qs of 10 and then higher than that eventually. Another very important parameter here is that you can think of the magnetic field as a force. It's holding the plasma from getting away. It's like a force that's confining it. And what it has to confine is the plasma pressure. And so a very important parameter on the lower right is the so-called beta parameter. That is that one looks at the ratio of the plasma pressure to the magnetic confinement pressure, which are classical quantities, the pressure of an ionized gas and then the magnetic field pressure from electromagnetics. And if you want to keep this system stable, clearly the stabilizing pressures have to be greater than the expansion pressures. And so that requires the beta parameter to be less than 1. But it turns out, in fact, it has to be significantly less than 1. It has to be on the order of 0.1 in devices that have been explored and developed to date. And finally, on the upper right, I'll mention that in order to create this system and keep the species hot, one requires heating mechanisms. And so one needs fairly sophisticated ongoing heating continuously into the plasma to counteract the losses which are occurring due to radiation and particle loss. And this is achieved by using both neutral beam injection and by RF heating at various different frequencies. And finally, what's causing your losses and even worse could cause disruptions in the system are plasma instabilities and drifts, which one continuously has to be monitoring for with diagnostic systems. Okay, next slide. So if one looks at sort of a catalog of some of this devices over the last few decades that have been developed, I won't go into details on the lower left here on the plot. I just want to point out that indeed, if you look at all the devices to date, the ratio of plasma pressure to magnetic pressure, beta, is on the order of 10 to 12% at best, and conservatively for better stability is on the order of 5 to 6%. And one can see here in the middle is ITER. That's get to that, the leading experiment in the world, this international experiment that's been developed as the benchmark for achieving net energy gain. And previous experiments, one of the biggest was the JET experiment in the middle. Okay, let's go on to the next slide. So let me just talk about the opposite direction. So instead of using magnetic fields in large volumes, to use instantaneous energy delivery, which we can do essentially with lasers or potentially with other ion beam sources. And these are called the inertial fusion energy approaches. And in the middle, one sees the simplistic picture of direct drive fusion, where you would have a fuel pellet on the order of a millimeter, a few millimeters in size, directly irradiated by many laser beams around the outside. And this would heat and compress the fuel, as I will explain in detail in a sec. An alternative approach, which is being pursued quite vigorously also, is to not use the laser beams directly, but as shown on the left, the so-called indirect drive approach is to shine the laser beams on the inside of a metal can, which now is about 1 centimeter in size, and the X-rays produced by those hot heated spots will then irradiate the fuel capsule, which is shown in the middle. And the reason for doing this is that one gets a very uniform bath of X-rays. And one of the key criteria, as we'll see, is that one compresses the fuel tremendously by the order of 1,000 times to a very tiny, dense hotspot in the middle. And in order for that compression to work, one needs a very, very uniform driving force. So uniformity is a key issue. And because of that, the indirect drive approach has actually been pursued as one of the major approaches to date. Next slide. So as I mentioned in the schematic picture of the various stages, one would irradiate the fuel from the outside with a uniform array of laser beams to make it very uniform. That would heat and vaporize the surface and ionize and form a plasma jet that's expanding outwards, just like a rocket engine expanding outwards, shown by the yellow arrows outwards in the second, and the red arrows indicate then the accelerated outer capsule accelerating inwards, and eventually the shell will collapse to the center, and at that point all of the material crashes together and produces a very hot, very dense hot spot, which is then where the ignition of the fusion reactions occurs, and that reaches the temperature and density conditions where the fusion reactions take off, and in so doing, as mentioned before, they will release energy in the form of alpha particles, which are trapped within the dense fuel, and therefore will lead to almost similar to a combustion wave, which goes through that core, and that wave then gives you a net release of energy, which is many, many times the energy that was actually invested in that ignition hotspot. And so with that, of course, we can produce net output of heat and energy. The picture on the bottom shows the similar process where you're radiating with laser beams coming in from the end of the can, producing hot spots and then causing the indirect drive. But essentially the process is the same. Okay, next slide. Okay, so one can look at just sort of the scale numbers for the different approaches. The magnetic fusion is continuous power delivery over tens, hundreds of seconds, and ideally fully continuous once one gets a cyclical current drive. And it requires typically on the order of about 50 megawatts of heater beams. This is what's envisaged for the ITER system coming up. Pressures on the order of 10 atmospheres and less. Power volume densities on the order of several megawatts per cubic meter, and wall loading intensities, power deposited in the wall on the order of megawatts per meter squared. So very intense conditions within the reactor. One looks at the inertial fusion side, one has very tiny fuel pellets, essentially starting at millimeters in size, compressed to final volumes of the order of 100 microns. Pressures which are just astronomical, 10 to the 11 atmospheres at the center hotspot, and driving laser pulse energies estimated and currently being investigated on the order of megajoules. The actual burn time is on the order of 10 to the minus 10 seconds, 100 picoseconds, and essentially this would be operated at a repetition rate of around 10 hertz, somewhat like a diesel engine. Next slide, please. And this then now shows a multi-decade sort of growth of the capabilities of magnetic fusion. It follows a Moore's law type curve where we see the performance ever increasing year by year, decade by decade. On the left is just the output fusion power in megawatts that's been achieved. On the right is the product of the Lawson criteria times temperature, which is another metric, the triple product. Either one, you can see that the curve essentially, there's on the blue line is Moore's law. It essentially is like the Moore's law in electronics. The problem is we started from such a small starting point. It's taking us this long to get to close to ignition and break even. Now the step sizes are becoming bigger. Essentially see the last point on the left curve is the JET DT experiment, which achieved a Q of 0.6. Our next goal is the ITER experiment, which should achieve a Q of 10. But these are major system, very expensive, large-scale systems, as we'll see, which are now incremental step sizes that will occur, but is coming within the next decade. Okay, next slide, just to continue. And this then shows the goal of ITER is just a different curve with Lawson criteria on the right and left on the temperature on the right, on the horizontal. And the goal is to get into the ignition condition with Q of 10 for ITER. And this, the International Tokamak project, which is a joint venture by most of the industrialized nations of the world, is a huge project. It's a $25 billion scale, 40-year project, started around 2005 and will continue probably around 2045. Next. And next. Okay, just to show you the scale size, the ITER tokamak cross-section is shown on the right. There's a little man in blue way down at the bottom on there standing. This will be a radius of 6.2 meters, major radius, volume around 1,000 cubic meters. Its goal is to produce net output power of 500 megawatts thermal energy, fusion energy, for a heater power of about 50 megawatts. And so that will be a Q of 10. And this would be carried out for durations on the order of hundreds to thousands of seconds. The previous generation is the joint European tokamak, the jet, which is down on the left, and similar size scale. And this one already achieved in the 1990s a Q of 0.65 and is being set up right now to try again deuterium tritium burn to achieve a Q of 1 or more this year, in fact. Next slide. This just shows you a picture on the right. This is real. I mean, this is one of the biggest science experiments of mankind to date. It's even more expensive than CERN in terms of the total budget, in essence. So it's real, it's under construction, and it's about 50% complete. First plasma will probably be around 2027. There'll be a number of years of optimization, and then actual fusion energy production will be about 2035. With DT fuel. Next. For inertial fusion, progress is almost at the same point. We're just short of the burning plasma conditions. So one of the lead facilities in the world is the National Ignition Facility, the Lawrence Livermore National Lab in California. Latest result from last fall was in fact production of neutron energy yield in a single laser shot of 160 kilojoules, which is still just about a factor of 2 away from ignition, but they've been improving their results by a factor of 2, about factor of 2 every 2 years, and so they are within striking distance now of getting ignition. If you remember my explanation, once you achieve ignition, burn follows, and the energy yield goes way up, so that if they get to ignition, then the yields start to become megajoules, and then you get into the Q of greater than 1 return on your laser energy going in. Next. This just shows you again, this is real. This is the picture of one of the laser bays on the left. The schematic of the building is shown on the right. This is several football fields in size. Laser bays on the left and right. The target chamber is in the lower right. So next, it basically is 1.8 megajoules. Okay, there are other approaches being pursued in parallel to sort of these major initiatives. For the tokamak, there's an alternative approach, which is the stellarator, which I showed earlier, which has twisted magnetic field lines. Instead of using the current to spin the plasma, they actually twist the magnetic field lines directly with the field coils. Requires significant engineering and precision on those coils to make the magnetic field lines connect properly throughout the loop. And this has been done. Wendelstein 7X is one of the leading ones in Germany at the moment. It would be larger volume than the tokamak, so it's sort of next in line to the mainline magnetic approaches for types. Next. An alternative is to go to much higher magnetic fields. So instead of the 5 to 10 Tesla now that are being pursued with the ITER projects, is to go to tens of Tesla to 50 Tesla fields, which is the goal of a number of startup enterprises, including Commonwealth Fusion, a spin-off of MIT, and Tokamak Energy, which is essentially a spin-off from Culham, and the JET project in UK, where they're pursuing new high temperature, ultra high field strength magnets to make the whole system smaller, more compact, more dense. And I'll get back to startups in a minute. Okay, next. For the inertial fusion side, there are also alternative approaches which are under development. One is to separate the ignition from the compression. So instead of operating like a diesel engine where you expect the fuel to compress and self-ignite, one can compress the fuel and then have a spark plug on the side. And then those are the concepts of fast ignition, where you actually use a separate laser pulse from the side through that cone aperture. Or to use a very intense shock driven by an intense laser spike at the end of your normal laser pulse, as shown on the right here. And so these would improve the efficiency of the ignition and the overall process, because the compression doesn't have to be done to the same level or precision as required for direct ignition. And so the gains are shown then on the next slide, where one can estimate, and of course these are numerical calculations, but I should say one of the reasons for the rapid or great progress in both magnetic fusion and inertial fusion over the last few decades is the the ability to do much more complex numerical modeling. And so this is an example of numerical modeling that has been done for these types of advanced approaches, where one's predicting Qs, target gain on the left, up to 200 and more for laser energies, which are on the order of 1 to 2 megajoules. And so these looks very attractive as long-term modes of operation. Next. Okay, so there are a number of startup companies around the world that have seen the promise of fusion and have jumped in quite significantly. And so we're seeing a lot of activity in terms of new concepts or improvements on present concepts. I mentioned the 2 Commonwealth fusion systems already, Tokamak Energy in UK. There's Tri-Alpha Fusion in California, USA. And of course, we have our own in Canada, General Fusion, moving quite strongly forward in Burnaby, BC. Some of these companies now are on the scale size of hundreds of millions of dollars, approaching $1 billion investments committed, and others are on the order of tens of millions of dollars at the moment. Next slide shows a few more. So there's also First Light Fusion, Oxford, that has started recently, Helion Energy in USA, and even Australia has one that's very forefront looking at the proton boron fusion using very advanced high intensity ultra short laser pulses of the future, HB11, which is also a startup with tens of millions of dollars of investment. Okay, next. What are the challenges? Well, the challenges are many, and on the right is just a schematic of what a full fusion power plant system would look like, with your DT plasma in the middle. The lithium, you need a lithium blanket around it to breed your tritium. You need a fuel cycle to extract the tritium and then manufacture new fuel pellets and then inject them back into the system. And of course, you need a heat exchange system to convert the primary energy into thermal steam generation is the main approach considered to generate electricity. Control of plasma instabilities is there for all of the different techniques. Just achieving ignition, scientific ignition, which is the goal of current experiments to achieve Q of 1 and greater, up to 10. Tritium breeding and extraction and recycling, processing of fuel pellets, that's a major technical development that's required. All the materials are going to be suffering neutron damage from the neutrons, which are energetic MeV neutrons in the case of fusion reactors. So developing structures, steels, materials, etc., that withstand this up to lifetimes, which ideally could survive tens to 100 displacements per atom lifetimes, which is very, very high. And then because this whole system is very activated in operation, servicing can only be done with robotics. So all of the robotic remote control servicing, designing it so it can be serviced and maintained over long periods of time. Each of these would require significant technical development, and ideally one should do that development in parallel on the order of 10 years of R&D per each element, I think, with also the investment of dollars that's required. Next slide. For example, reactor materials. There's been significant work over the years to identify materials which have very low activation so that they would then lead to very minimal radiation and decay lifetimes after decommissioning of plants. If one looks at the green curve, those would be particularly good vanadium steel alloys, which are then least activating of the typical alloys available to date, which would require 10 to 100 years to recover to below baseline or acceptable levels for waste disposal after a plant is shut down. There are other materials which are futuristic, like silicon carbide, which in principle, if one could develop the systems out of silicon carbide, then their activation levels would be minimal, and those would be ideal materials. And perhaps with 3D laser printing and other manufacturing techniques to date, one could consider making real reactor vessels out of such materials. So that's one example just of technologies that one would need. Next. Okay, so just to finish with sort of more specific challenges for each of the approaches. For the magnetic fusion, there's one major plasma disruption which can occur, which is called a major disruption, where the plasma will short to the wall, a significant perturbation in the plasma behavior. This can be tracked by diagnostic systems and mitigated by rapid injection of essentially cold gas pellets, which will cool the plasma faster than it can cause damage. The whole area of developing high temperature, high field superconductor magnets for these compact toroidal devices is very active at the moment. The fueling and injection of the deuterium tritium fuel pellets is still an area which needs development. The radiation damage of all of the material systems, complex systems near the reactor core, such as cryogenic magnets and control and diagnostic and heating systems, needs development work. And of course, this extreme power that's being deposited on the walls, particularly on what's called the diverter plates at the bottom of the reactor, where a lot of the energy comes from following the magnetic field lines, where the loading is at the point where it would basically melt most materials. Okay, these are being addressed in ongoing programs around the world in the various magnetic fusion energy activities. If next slide, we look at the inertial fusion, it has its own set of specific challenges. One of them is just the laser plasma instabilities, which are still causing a degradation in the efficiency of coupling of the laser light to the plasma, and also causing instabilities in the compression. These are at a controllable but at a significant level, and one of the mitigation strategies is to change the laser drivers to make them much broader bandwidth to reduce the coherence. And this is what's anticipated for the next generation of laser systems. High efficiency is also required in the lasers, but that has already been developed, primarily driven by industrial applications, which now use very high efficiency diode pumped lasers, which can achieve wall plug to light efficiencies much greater than 20%. One needs, of course, all the optical components that would withstand this continuous onslaught of laser pulses day in and day out at very high intensities. So high damage resistant optical components still need more development. And one of the things, of course, since you're injecting a fuel pellet every shot 10 times a second, is these fuel pellets have to be produced en masse with precision, filled with fuel at a very low cost. And so mass production techniques using microfluidic and other manufacturing techniques are required. And again, a lot of these challenges are recognized, are being addressed on ongoing programs around laser facilities around the world. Okay, I think that's the end of my slides. If we go to the next one. Yeah, so we'll switch back to Axel. Thank you.
Thank you very much, Robert, for the deep dive into the science and technology of fusion and making it happen. Let me now return to some general fusion topics, starting with business challenges. But the first issue that comes to mind is funding to make fusion with a net gain in energy happen. The ITER project alone is valued at more than $25 billion and is therefore largely in the hands of government. However, the private sector is also stepping up with major investments, such as almost $1 billion for TAE's work in the United States. And General Fusion, which Robert mentioned, a British Columbia-based company, has raised substantial funds from investors, including oil and gas companies. However, much more funding is needed to advance fusion. The returns are high, even in the developmental phase of fusion. This has been confirmed by several studies, including a recent UK report that showed that an investment of about £350 million yielded about $1.4 billion in economic benefits. Next. Personnel is a critical requirement for fusion business success. Personnel is not only needed in the core disciplines of plasma physics, but also in many other scientific disciplines like laser technology. In Canada, many of these disciplines require much greater support than they're currently receiving. And I'll say more about that in the next slide. Next, please. No business can prosper without strong market opportunities. In the case of fusion, the focus has been on energy markets, which are important, but by no means the only important markets for fusion. Again, I'll say a little bit more about that in a moment. Next, let me conclude with the fourth key business challenge, namely business strategy. Such a strategy includes not only industry, but also government and academia. I characterize such a strategy as active patience. While we must be patient, patience does not mean sitting back and observing what others are doing. We in Canada must be active participants in fusion development and the uses of fusion products and services. Next. I see the Fusion Energy Council of Canada as taking a central role to help meet these four major business challenges. Next. However, these challenges are so large and they're all connected, so that FECC cannot address them by itself. We therefore want to address the challenges with partners, particularly OCNI. But there are also other partners in Canada and abroad with whom we look forward to collaborating. Next slide. This slide shows the main implications I see for Canadian industries. Fusion is clearly a new high-tech sector with enormous opportunities. Many of the opportunities lie in scientific areas like materials. Recall what Robert mentioned about neutron-resistant materials as one example. However, there are other major immediate opportunities also in finance and insurance. Most fusion projects will be large, meaning that there are great needs for engineering, procurement, and construction services. Canada has several outstanding companies in the EPC sector that can contribute to fusion development and implementation. We are all aware of the need for electrifying the transportation sector. Electrification calls for carbon-free energy. What is not so well understood is that the availability of electricity and heat from fusion plants will also enable new electrochemical industries that go well beyond today's production of metals and basic chemicals. And finally, environmental sustainability and the circular economy require copious quantities of energy and in particular electricity. Fusion will support circularity. Next slide. Let me now briefly state the implications of fusion for Canadians. Clearly, fusion and its applications will create many new jobs. Next. However, it will also displace existing jobs in some industries. Job transition schemes are therefore necessary and need to be thought about early and well before jobs in affected industries are lost. We can do such forward planning in Canada, but we rarely do so. Next. Fusion will provide Canada with energy security without primary reliance on the combustion of fossil fuels. This will make Canadian manufacturing products more competitive as the price of carbon is incorporated into products and services worldwide. Next. And last, but by no means least, fusion will enhance Canada's environmental quality. There will be direct benefits from carbon-free energy production. However, there will also be indirect benefits. One example is waste recycling, a process that is inherently energy intensive. And the next slide. Then based on what Robert and I have presented, we can draw the following conclusions. First, fusion energy and uses will become new realities with great potential, but also still posing great challenges. Next, Canada must participate in creating the new fusion realities in order to reap the rewards. Thirdly, partnerships and collaboration accelerate fusion realization. And fourth, nuclear fusion and nuclear fission are symbiotic sectors. And lastly, FECC and OCNI, in my view, are symbiotic partners with great futures as we work together. Well, ladies and gentlemen, this concludes our presentations. and we can now move into the question and answer period. Let me therefore welcome Professor Allan Offenberger. Allan is a Professor Emeritus with an outstanding academic career and with extensive expertise in nuclear fusion and the associated fields. He has kept fusion in the conscience of Canadians for several decades, and he has fostered many connections between Canada and fusion experts in the United States and elsewhere. Without Allan, I believe, today's event would likely not have happened, and Canada would not be so well positioned for entry into the new era of fusion energy. So welcome, Allan. The participants to this webinar were asked to submit their questions via the chat feature, and I'd like to call now on Rachel Roberts to present some of the questions to the panel that consists of the three of us, or Ron may also participate, so we're really a panel of four. Rachel?
All right, thank you, Axel. And thank you, Axel and Robert, for that wonderful detailed presentation. We have a few questions here. So one is, what role will Canada play in the supply of tritium as fuel to the various projects and handling technologies to support the entire fuel cycle?
Okay, maybe I can respond first. Canada recently signed a collaborative agreement with ITER, the project that Robert mentioned. And as part of and at the core of this collaborative initiative is for Canada to supply tritium. And the tritium production is closely linked to the CANDU fission technologies that we have and the production of deuterium. Allan, do you want to add to this, and maybe Ron as well?
Okay, I could just amplify that a bit. Am I heard?
Yes.
Okay. By just pointing out that when Axel referred to a lot of the elements that have to go into our future activity in fusion, it needs people, it needs enabling technologies, it needs industrial capacity. And so in the sense that we already have a tritium capability that's going to be very important, that's a key component of any fusion system. We also have a lot of enabling technologies that are emerging. General Fusion as a company that's already actively involved. So you've got both the combination of enabling technology development plus manpower skills being developed. And to add to that, you have major university programs such as at the University of Alberta, University of Saskatchewan. You have people, you have products, and you have, along with the skill sets, the industrial capability emerging. There are also a number of smaller firms emerging in Canada that are already delivering, whether it be instrumentation or MEMS and other products to the research and development field. So it'll be expanding on all of these that will lead to the effective introduction. Plus, we have the long-standing skills of the nuclear industry, particularly in Ontario, where a lot of this, when you go to build big systems, all of this capability and handling of materials and radioactive waste are important. So that's just a few additions.
Yeah, and tritium is actually a very nice example of the symbiotic relationship between fission and fusion.
Yes,
it's required in both cases,
Yeah.
in Canada's case, due to the CANDU system.
Mhm.
Yeah, just to amplify that, ITER on startup is going to need the kilograms of tritium that they don't have, and so Canada is going to have to be an important supplier to initiate the first experiment when ITER gets around to DT burning.
I think another comment, maybe just to finalize on that, is that, in fact, with a lot of startup companies envisaging demo reactors of their own, the demand for tritium may well outstrip the supply, because every startup essentially consumes tritium. It's not a breeder system yet, and it's not producing tritium. So they're all going to make inroads on the tritium supplies, which are very limited. Yep. So it's a very valuable commodity.
If I can add to that, it would be a nice problem to have, because we're making tritium every day
Exactly.
as our CANDU plants operate. But I just want to go back to the supply of tritium story. As I know the gentleman on the panel would know, and maybe a few of our more seasoned audience members would know, Canada came very close 20 years ago to landing that big project that you showed a picture of in southern France, the ITER project. We put in a serious bid, or Canada put in a serious bid to host that project at the Darlington site, which is just around, which is where the tritium is located. And we had all the other attributes that you mentioned. I mean, personnel, technology, power supply. And I'm wearing now, this is one of the few existing ITER Canada t-shirts that I happened to snag from Don Donovich, and gentleman escapes me when we signed the MOU. So that's the front of the t-shirt, and you can see in the back. So it would have been a wonderful project, and I think Adrian Foster is on the line. I saw his name. Adrian was very much a part of that team representing Clarington, the area in which this great facility would have been built. So were it not for, I guess, the fact that we were outcompeted by France, we could be hosting this webinar from the from the ITER project near Darlington. So we have these great attributes, and thanks to gentlemen like yourselves, we're trying to get back involved in the game. The nuclear cooperation agreement between Canada and ITER will soon be ratified by the Canadian Parliament, and that will give us the means by which, the safeguard means by which we could theoretically export tritium to the ITER project in southern France, and that would take place probably in the early 2030s. They don't need our tritium for a few years.
Okay.
Well, in fact, a follow-up on the ITER not being sited in Canada. In fact, as we go through generations of prototypes with alternative technologies, Canada could become a site once again for these demonstration projects.
For an improved, smaller version.
Yeah, and there will be many, several are already under consideration. The United States has called, the National Academy of Sciences, Engineering and Medicine has called for a demonstration project. China is in the advanced stages, so we will see more than one demonstration project.
Actually, since I'm got the mic and I'm not turned off, can I ask a related question? In your last slide, you talked about the key part that personnel will play. Are you guys seeing a lot of interest at the University of Alberta, young engineers wanting to take plasma physics and fusion courses at the University of Alberta?
I would say yes. I mean, pretty well all the students that you talk about fusion to really get excited about it. So there is some uptake, but again, you must understand students go to where they see the job opportunities. So if we have a fusion project, I think the number would go up a factor of 10. Until we have some significant activities. I mean, there are many who are interested, but they're still considering what are they going to do in their careers and looking at what the opportunities are. So, I mean, it's a chicken and egg. We need the significant projects in Canada to attract the people also. But definitely, I mean, if you ever talk to a student about fusion, the spark lights immediately and they say, wow, I'd like to get involved. Yeah.
It takes me back to an earlier time in my life when I took a plasma physics course at Princeton from Lyman Spitzer, whom I'm sure you guys have heard of, and Allan Gottlieb, the two guys that were running the Princeton Plasma Physics Lab a good number of years ago. I'm sure they both left us by now.
Yeah. Okay, thank you, Rachel. Do we have other questions that we could pose?
So one is, lately there was news from Princeton that electrons cause significant turbulence during the fusion process in MCP. Can you elaborate?
Okay, that's a very technical question, so I'll leave it to Robert and Allan.
I thought Rachel could answer that one.
Maybe I can comment on, Allan can add some. I mean, basically, as we said, the plasmas are very complex systems, and turbulence is one of the major aspects, which is very difficult to model mathematically, and even now is a challenge for the numerical modeling. So indeed, that's one of the areas still that needs to be, I would say, understood better, and certainly what Princeton is doing is the ongoing work to really clarify the role that turbulence plays and how it affects the diffusion of energy, loss of energy, etc. But without going in, I don't know the specific report, but I don't know specifically the details. But in general, turbulence is an important aspect. Yeah.
Yeah. In a general sense, there's nothing for me to add. It is turbulence, and it's the micro fluctuations that happen, particularly on the edge of the plasma, that lead to these losses. And both numerical simulation and experimental approaches are finding ways to tame them down, let's say. So it's ongoing research.
Yep. But a solution or a set of solutions will be found. I think we can be quite confident about that. Okay, Rachel. Do you want to go to the next question, Rachel?
Yes. So one of the main problems I see is the significant parasitic losses of highly structured energy is injected to produce low-grade energy. This will make the balance of plant very expensive per grid output. Is there a way around this?
I'm trying to understand the question exactly. I mean, we are creating energy and we're recycling it into heat and then electricity, and then using that to form very, as you say, highly organized, like laser beams or RF power injectors, etc. But the efficiencies of those processes is fairly good. So, as long as your Q is greater than 10 or more, you basically make up the net balance of loss of energy. And I don't think we worry about whether we're creating, too much entropy in the process, so long as we get the net balance of energy. Now, maybe Allan had some other thoughts.
Yeah, no, and that hits the principal answer. I guess the question I'm trying to understand from the person is why is it we have to go through very sophisticated, high quality, like photons from lasers or RF in fields to be able to end up just getting heat at the end of the day. But we do get more than that because when the products come out as neutrons and helium and the liberation of energy, because it can be done efficiently in the sense that if you just take lasers as one example, as Bob alluded to, we already have lasers that are 20% efficient. So I don't consider it necessarily an undue high quality input to get low quality heat out at the end of the day. It's an overall energy conversion, and we do that all the time in society.
Yeah, and there is a demand, a copious demand for electricity as well as thermal energy. If you think about a diesel engine, which is under good conditions, maybe 30% energy efficient, imagine a world without a diesel engine today. Much of the heavy machinery that we depend on, trenchers, front-end loaders, etc., just wouldn't exist. So efficiency is important, but it's not the only thing to think about.
I think what the questioner was maybe getting at is the technical challenges of converting and streaming and manifesting energy and pressure in a way to achieve fusion is really enormous. This is probably the most challenging scientific task that mankind has ever undertaken. And I guess they're simply saying, I hope it's going to be worth it in the end. And obviously we all believe it will be, otherwise we wouldn't be on this panel. But compared to nuclear fission, which was really relatively easy compared to what's been happening in fusion for the last 50 years.
Yeah. But the need for energy is major, and will continue to be major. The question is how to produce it given all the other constraints under which we are operating, and carbon and greenhouse gases are just one set of constraints. Interesting question.
Yeah,
Rachel?
All right, next question is, fusion seems to be at the stage that requires more engagement outside of the industry and academia. Can you tell us what FECC is doing in the areas of government relations and regulatory affairs?
Right. So if I can speak on behalf of FECC, we are in the process of developing our strategies to engage constructively with government, because governments do have to be one of the major funders, not the only funders in the near term. But that is what we are currently involved in. Our focus is naturally on governments in Canada, but we also have connections through our advisory group with governments elsewhere. And we very much would like to undertake this approach to government in harmony with organizations such as ONCI, because we don't want to create a misalignment of messages. Each one of our areas has its own footprint and domain. So that strategy of approaching government for support of fusion developments in industry and in academia and within government itself, that's our top priority within FECC.
Axel, did you see the question from Herminia Roman?
Yes,
No,
that's an excellent one.
I did not. So
Okay, she's asking, given that we have an International Fusion Research Council within the IAEA framework, the International Atomic Energy Agency, is FECC going to be looking at participating through that, joining that body?
The answer is yes, we are considering it. The question is, how would we participate in it? Because if we do participate, we want to be active participants. We just don't want to have our name on the list of participants, which in turn means identifying areas of needs that are particularly well suited for Canada and also meet the needs of IAEA.
Okay. I'll just add one little comment on top, and that is that given that fusion has been a multi-decade, principally driven by the need to understand the science, the computational capabilities, building of enabling technologies, and so on, we've really reached an important time in the sense that we not only have mainline approaches getting near success, but we have a lot of alternative proposals in technologies and in terms of approaches to practical fusion. So we're at a very propitious time that, and let me just take by example, the US, if you look at what's been going on for multi-decades, it's been almost just a big science project rather than an energy driven motivation. That is now changing. We have the NRC in the US looking at the regulatory aspect. We have Congress and Senate looking at funding and moving the US ahead. We have China very aggressive in fusion. We have Europe and Asia that have for long standing had fusion at the center of energy policy. So we've sort of just reached the point where I think it's going to give us a lot of opportunity to do all of these international liaisons and arrangements with a lot of bodies. So to Herminia, I think what Axel has said is important in the context of what's happening all over the place internationally.
Yeah. I am conscious of the time. We are 5 minutes over our allotted time, and I think I should bring the webinar to a conclusion. If there are further questions, please share them with us. But let me circle back to the analogy with which I started. It took about 100 years in order to develop human flight from what the Wright brothers did to where we are now. In fusion, we are maybe 30, 40 years into the development. It will take some time yet, but we know how to accelerate technological progress, especially in areas that are critical, not only for economic well-being, but for environmental sustainability, not just for a country, but for our entire world. And I think fusion can make an important contribution, as can other fields of energy production. So I thank you for your participation. Ron, I thank you and OCNI for having hosted this event. And since you opened it, let me turn it over to you for the final word.
Well, Well, let me just conclude by saying I thought that was an excellent, fascinating, informative presentation. It's the best walkthrough I've ever seen in fusion and the challenges that we face. So I really commend the team. I commend what you're trying to do. My only regret from today is I wish we had pushed this out to the universities. I know we have some people from McMaster and Ontario Tech and maybe others, but it's maybe the next time we do this, we will make sure that the invitation goes out to students. They may be in the middle of exams right now, which could be a problem, but I think it's the next generation of young people that really need to be inspired by the vision and the passion that the three of you demonstrated today, and also the vision of a world with enough clean energy that we can sort of ensure that people around the world, not only those in the developed countries, have access to clean energy. So I thought that was a fascinating session. Thank you, Rachel, for being a very accomplished moderator again today and host. And maybe we could say a couple words about what we will talk about in our FECC-OCNI seminar number 2.
Right, if you'd like me to respond, the focus will be on the business development, so really practical steps.
Sure,
having
yeah.
set the stage today by giving background information, what is fusion about, how can one think about it? Now, what do we do, and what do we do collaboratively? Would be our intention to explore it together with you, and right.
And we'll ask people to bring their checkbooks.
Yes.
Okay.
Checkbooks on time.
Okay.
All right.
That was wonderful. Great seminar. Thank you to all of our participants. Sorry we're a couple of minutes over, but this was just too compelling to stop it early. So thank you, Robert, Allan, and Axel, and Rachel, and all those on the
Thank you very much indeed.
Okay, thanks everybody. Bye-bye.
Goodbye.
Thanks.
Good day.
Thank you.
Bye-bye.